So I'm going to call this chapter Chapter 6. Obviously, anything we're doing today won't appear on the test because the test is the Chapter 9 stuff. Cool? Okay. So Chapter 6 is about radical functions. So when we say a radical function, what we mean is something that can be written in the form y equals a times the nth root of x minus h plus k. And we say that that symbol there's the nth root for n greater than 1 and an integer. So n can be things like 2, 3, 4, 5, 6. It can't be like 1.7 or -3 or something like that. So far, so good? So what we're going to spend most of today talking about is just kind of how to use this nth root. So we'll start by just kind of talking about simplifying and just run through some examples here. So let's say we were asked to write in reduced form the square root of 72. Well, the goal here would be to find a way to rewrite the square root of 72 so that it's the product of a perfect square and something else. So does anybody see a perfect square that's a factor of 72? So remind us the numbers that when I say a perfect square, let's remind us what we're talking about. What's an example of a number that's a perfect square?
64.
64, because 8 squared is 64. Okay. What else is a perfect square? 9, because 3 squared is 9. What else? 4, because 2 squared is 4. What else? 16, because 4 squared is 16. Good. What else? We said 4 already. 25, because 5 squared is 25. Keep going. Yep, Edmund. What? 144, because that 12 squared is 144. Any others that we can think of? We still haven't found the one that I'm looking for this problem. 36. 36 squared, or 6 squared is 36. And I notice that 2 times 36 is 72. Everybody okay with that? And so, because this is multiplication going on underneath my radical, I can break the radical at that multiplication symbol into two radicals. So square root of 2 times the square root of 36. And the square root of 36 is just 6. So I can call that 6 root 2. Everybody okay there? Now, we were lucky because 36 times 2 being 72 is relatively easy to see. But what if I'm not very good at that? Right? Can I approach that from a different way that's maybe a little bit more systematic if I'm not good at just seeing factors like that? Because some of us aren't, right? Some of us have trouble looking at a problem going, oh, 2 times 36, that's what I need, right? So alternatively, what you could do is you can write 72 as a prime factorization. So 72 is 2 times 36. And 36 is like 2 times 18. And 18 is like 2 times 9. And 9 is like 3 times 3. So I can go ahead and group these into pairs. And I have 1, 2 that can't be paired. So I can say then the square root of 72, I could think of as the square root of 2 squared times the square root of 2 times the square root of 3 squared. Everybody okay with what I did there? And so that just becomes 2 square root, 2 times 3, and we can multiply in any order we want, so we can just make that 6 root 3, or 6 root 2. So you can think about it that way also, right? Some of us, it's easy to see the perfect squares. If we look at some of these bigger nth roots, like a cube root or a 4th root or 12th root or something, it's much less obvious. Oftentimes it's less obvious, like what numbers are we really looking for? It doesn't really matter. At that point, you're just doing a prime factorization. Okay, let's do another. Yes? So let's say we're doing a cube root of 256. So here, we're looking for perfect cubes, right? Since we're dealing with a cube root, what's an example of a perfect cube? 8, because 2 cubed is 8. Great. $27, excellent, because 3 cubed is 27. 64, because 4 cubed is 64. So this is much harder, right? These are not quite as easy off the top of our head to come up with. And I think that as that value, or as our nth root, the index there gets bigger and bigger and bigger, this becomes a more and more challenging exercise to do just ad hoc like this. And I think we often are going to be better served by just doing a prime factorization, which is what I'm going to do for this problem. FYI, 64 would have been the one that we wanted. So 2 times 128, 2 times 64, 64 times 32, 32 times 16, 16 times, or 2 times 16 is 8. I meant 2 times 8 is 16. 8 is 2 times 4, and 4 is 2 times 2. And so now I'm trying to package these into triplets because we have a cubed root. And then we have a pair that just can't do anything with. Okay with that? So we can say this is the cube root of 2 to the third times the cube root of 2 to the third times the cube root of 2 squared. Everybody so far so good? Okay. Cube root of 2 cubed is just 2. And cube root of 2 squared we can't do anything with. So let's combine the 2 times 2. And we're just left with like 4 cube root 4. Is that okay? Okay. What if we had asked you to do instead? Well, let's just make a little observation here at this point. So the square root of -1 is equal to what? Think back to chapter 4. It just equaled I, right? Yep, good. What's going to be the cube root of -1? It's just -1, right? Because -1 times -1 times -1 is -1. Everybody's okay with that? So the takeaway here is the nth root of anything is a real number when n is odd and a is negative. And the nth root of a is not a real number when n is even and a is negative. So we can take odd roots of negative numbers, but we still can't take any even roots of negative numbers. Everybody's okay there? With that idea? Should match up pretty well with that observation we just made there. Okay. Let's do a fifth root of negative 2048. Am I going to regret that? No, I think that's okay. First things first, does it matter that it's negative? Well, it's an odd root, right? So it's okay that it's negative, no big deal. If you really want to think of, if it's really troublesome to think about, you can always do that. And I know -1 is the same thing as -1 to the fifth. Right? -1 times -1 times -1 times -1 times -1 is still -1. Cool? So I can just always know that I'm going to get -1 times whatever that answer is. Everybody cool there? So we just have to do basically the fifth root of 2048. So I'm going to go ahead and do my prime factorization. Again, if you know how to break that up into a perfect fifth power, cool. If you don't, I don't blame you. I don't think it's terribly obvious what to do. I don't know that most of us would be able to name any powers of 5 right off their heads other than 1. And you notice that I always, when I do this, just kind of use the smallest prime that I can come across right away. So if I have an even thing or whatever, I'm just going to do 2 and whatever else I get. Now, how many am I looking to package together? How many 2's do I want to package together? I need 5 of them because this is a fifth root. So there's 5. And there's 5. And we just have 1 left over. So we have the fifth root of 2 to the 5th times another fifth root of 2 to the 5th times the fifth root of just 2. So we have -1 times 2 times 2 times the fifth root of 2, or -4 fifth root of 2. For those of you keeping track at home, we would have had 1024 was our power of 5. It was 4 to the 5th. But, good Lord, none of you probably were going to come up with that anytime soon, right? The prime factorization, though, makes it pretty easy. Now, it takes a minute to write the prime factorization out. It takes a little bit of time or a little bit of space on our paper to write the prime factorization. But it's not difficult to write it. You know what I mean? You're just doing basically like whole number divisions. You know what I mean, guys? What do you think on this? Is this okay? All right. So the other piece that we would like to be able to do is we'd like to be able to, so this is just simplifying, right? We're just taking a single radical and breaking it up into something simpler. In that, we're able to pull out any whole numbers that we can. That's what we kind of mean by simplifying, right? We take whatever's under the radical, and we can pull some of it out front. Yes, that's clear what we're trying to do there. There's other kind of simplifyings that we were going to be interested in doing. What if we want to multiply 2 radicals together, or divide 2 radicals, or add or subtract 2 radicals? So that's the next stuff. I'm going to start with just adding and subtracting. So first things first, let's say we have the nth root of A and the mth root of B, where m and n are not the same number. And they're reduced already. And then there's nothing to do. You can't combine 2 radicals that are different if they're already been fully reduced. There's nothing to do. However, if I had the nth root of A plus the nth root of a. This we can do. And it just becomes 2 nth roots of a. If I have the nth root of a plus the nth root of b, here, there's nothing really nice to do. I mean, there's some sneaky stuff that you might want to be able to do, but like, for example, if we had like something like this, if we think about the cube root of 4 as cube root 2 times cube root 2, we could like factor the greatest common factor of cube root 2 and do something like that, but I would argue that's not made it any simpler, right? Here again, I would say there's really nothing to do. I want to point out that there is like technically stuff you could do that might make, you know, if you have like a fraction going on, you might be able to do some clever factoring to cancel something that could be helpful, but by and large, like, you wouldn't want to actually do that unless you had some broader simplification plan in mind. Is that okay with you guys? So again, I just wanted to make clear when I say there's really nothing to do, I mean there's like nothing productive to do if the problem is as simple as that, right? If it was part of some bigger thing, it might be helpful to do that factoring so you could cancel something, but by and large, it's not going to be real helpful to us. So let's look at a couple of examples here. So let's say we have the square root of 8 plus the square root of 128. As they're currently written, can I add these together? No, because the stuff under the radical is different, even though they're the same radical. However, do we know if these radicals are reduced? We do not know that, right? So let's check to see if we can reduce them, because we might be able to reduce them down so that the part underneath the radical is the same, and just the coefficients are different. Everybody okay with that plan? Okay, so the square root of 8, I'm just going to think about as 4 times 2, because 4 is a perfect square. That one should be easy to do in my head. I don't need to do a prime factorization to do that, although if you wanted to, that's totally fine. Everybody's okay with that? 128 is 2 and 64, which is 2 and 32, which is 2 and 16, which is 2 and 8, which is 2 and 4, which is 2 and 2. So I have 1, 2, 3 pairs of 2s, and then 1 left over. So I have 1, 2, 3 pairs of 2, and then a square root 2 left over. So square root 4 is 2. And then I have 2 times square root 2. So there's that. And now can we add these together? Yes! We just get 10 square root 2. Man.
Why? Oh, never mind. It's my own question.
Okay. That's the best kind of question. I love it. Does that make sense to everybody there? So you really have to be careful that when we're asked to add 2 radicals and you're like, oh, no, you can't do that. Are you sure you reduce the radicals? Are you really sure?
But do you have to, like, because 128 was being divided by 2, do you have to do that since that's what you got with the square root 8?
typically when I'm looking for a prime factorization, I just start with checking to see if the smallest prime is a factor. The smallest prime number is 2. So as long as I got an even thing, I'm just going to keep dividing by 2 until I can't do that anymore. Then I'll try 3 or 5 or 7 or some of the other bigger primes. But I typically just start with 2 because that's the smallest prime. And the fact I kept getting, like, when I divided by 2, kept getting even numbers, I was just going to keep dividing by 2 until I didn't get an even. Or I was out of things to divide, until I got it. Or until it gave me 2 also. Like, in that case, I know I'm done. Does that make sense? So it really had little to do with the fact that there was a square root of 2 under the other one. I mean, I was hoping that that would be the case. But, I mean, if this was like, like 108 or something instead, you'd have, or not 108, I'd want like 162 or something. There you would have like square root 81 times square root 2. So there you could have divided by 3 a bunch of times and ended up at the same spot. But anyways, that's the big takeaway with adding and subtracting. So we just got to be careful. Okay with that? The other place where we might have to be careful is, let's say we had, we can't do that yet. Sorry, nope. Let's go and look at some other situations. We'll circle back to that though. So multiplication and division. As long as the radical part is the same, we can stick them under the same radical, or you could use these rules in the reverse direction and take something under one radical and break it into many radicals. So for example, if I have the square root of 12 divided by the square root of 3, I can just rewrite that as like the square root of 12 over 3. And 12 over 3 reduces to 4, which is just 2. And oftentimes doing that is going to be easier than trying to break the radicals up individually, especially if I can see there's reducing that's possible. Like I'm going to stick them under the same fraction, reduce, and then go about my business afterwards. Is that okay with you guys? Make sense? So here's the question for today. What if I want to do something like this? What if I want to multiply the square root of 2 by the cube root of 2? There's a way to do this. So let's talk about how to do that. So to do this, we're going to have to define a new way to conceptualize a radical. So our new definition for a radical is that the nth root of a to the m is going to be the same thing as as a to the m over n exponent. And you might say, okay, like big stinking whoop, what does that do for me? Well, recall all the way back to your Algebra 1 class, your rules for exponents. So there's a product property. It says like a to the n times a to the m is equal to a to the n plus m. You guys remember that? Like x squared times x to the third is x to the fifth. There's the power of a power that says like a to the n to the mth is a to the m times m. Right? Like if I take x cubed squared, that's going to give me x to the sixth. Because basically I have two sets of x cubes. We have power of a product that says a times b to the n is a to the n times b to the n. Note that you must have a product for that property if you have addition or subtraction going on between the a and the b. No dice. Exponents do not distribute. And again, hopefully that's clear. Like if I have, 2x quantity squared, that's 2x times 2x. So I have a 2 squared and an x squared, right? Let's see, we have the quotient property. If I have a to the n over a to the m, that's a to the m minus n. Which again, like if you have a fraction with x cubed on top and x squared on bottom, the 2x's on the bottom can cancel with 2 of the 3 x's up top, and you're left with just 1x left over. You have power of a quotient, which is basically the same idea as the power of a product property. So again, think about it as if like you're doing 1/2 squared. That's just 1/2 times 1/2. So you multiply the tops together and the bottoms together, you have 1 squared over 2 squared. There's the zero exponent property. It says a to the 0 is 1, assuming that a is non-zero. I guess this other one I have to say that b is non-zero. And this one, a is non-zero. Again, you can't have a zero denominator is basically all we're saying there. And I think that's it. So, if we take these properties together with our new definition for an our exponential definition for a radical, we can deal with square root of 2 times square root of, or cube root of 2. So let's return to that. Oh, there's one more I forgot. There's the negative exponent property. It says a to the negative n is 1 over a to the n. Again, where a is non-zero. I thought I was forgetting one. I was like, no, I got them all. And then pulled the Kulik. A minute later, you're like, oh, no, that's not all of them. Sorry, guys. I'll pause here a moment as you're trying to rearrange some of your notes to get these my scribbly scrabblies in the right places. I know it's irritating. I apologize. It's not my fault. I mean, it is my fault, but I didn't do it on purpose. You know, it was an accident. People make mistakes. Happened to me. Okay. So I'm going to take a moment and just fill in some of these missing pieces, because not everything we wrote down when we write down like the square root. The index here for a square root is 2, right? It's square root, so the index there is 2. And the exponent on the 2 is a 1. We know it's there even if we don't write it. Oh my goodness. Oh my goodness. So using that exponent definition, I have 2 to the 1/2 times 2 to the 1/3. Everybody okay with that? So here the n is 2 and the m is 1. This one the n is 3 and the m is 1. So if I use my product property, that means I really have 2 to the 1/2 plus 1/3. To add fractions, what do I need to have? Common denominator. For 1/2 and 1/3, the common denominator would be 6. So 1/2 becomes 3/6, and 1/3 becomes 2/6, and we add them to get 5/6. That's a hard word to say. And when I rewrite that as a radical, I have the 6th root of 2 to the 5th, or if you'd prefer, the 6th root of 32. Which is a rather surprising result when I take square root of 2 and cube root of 2 and I multiply them together and I get the 6th root of 32. Seems kind of bonkers until you're like, oh, okay. Well, if I'm just using that definition, it's not a big deal. So far, so good? Okay. So let's do some terrible examples now. Or actually, let's talk about the standard way in which we write our answer. And then we'll do some terrible examples. Okay. So when we talk about a fully reduced radical expression, we should have no negative exponents. Any negative exponent should be converted to turn them into positive exponents using property number 7. Should have no radicals in the denominator. You guys probably remember that rule from geometry last year. That was something that we talked about. Remember, how did you get rid of radicals in the denominator? What was the name of that process? Do you remember? Started with an R. It's called rationalizing the denominator. you remember that name? Okay, so that rule still kind of holds here. Then we should say that each individual radical is reduced all right. I think that's the criteria that I want there. Let's do an example. So here we're going to get into some nasty simplifying examples here. Okay? So some of these are going to be gross and kind of terrible. But we'll go through them slow. We'll step through them together. So typically what I like to do on a problem like this, we'll notice that I have 3 different kinds of radicals, right? I have square roots, I have cube roots, and I have fifth roots. Everybody notice that? What I'm going to want to do is eventually I'm going to want to convert everything into a rational exponent so I can get these all together in one expression. But before I do that, I'm going to start just by doing a prime factorization for each of the coefficients. Is it okay if I do those prime factorizations in my head? Okay. If you need me to write it out again, I will, but that's all I'm doing, is just kind of drawing that factoring tree. That is, oops. I think that, right? Let me just double check that right quick. Oops. Yeah. So far, so good. Yes? Okay. So that first one is going to become 2 to the 3 halves times x to the 5 halves times 3 to the 4 thirds times x to the 2 thirds all over 2 to the 3 fifths times 3 to the 3 fifths times x to the 1 fifth. Everybody comfortable with how I've moved to here? So all I did is I went and converted each of these into fractional exponents. And now I'm going to combine them together. So the 2's I can combine together. The 3's I can combine together. And then the x's I can combine together. Is everybody okay with that plan? Okay. So for the 2's, I'm going to be using the quotient property. So I'm going to have x to the 3/2 minus, 3/2 minus 3/5. Sorry, that's a 2, not an x. The 3's, again, I'm also going to be using the quotient property. So 3 to the 4/3 minus 3/5. So far, so good. The x's in the numerator, I'm going to combine using the quotient, or I'm sorry, the product property, and then the one from the denominator using the quotient property. Notice no more fraction, which is pretty good because that means there's no denominator to have a radical in. But we'll have to be a little bit careful when I finish there to make sure that that is still the case. Because I could end up with a negative exponent somewhere along the way here, right? Because we still have some subtracting that we need to do. Is this okay? Again, stop me if I'm going too fast or you need me to slow down or you're not quite sure what I did or want to double check something or whatever. Okay. So to add or subtract these fractions, we're going to make common denominators. So in the 2, the common denominator would be 10. So I'm going to have 15 over 10 minus 6 over 10. In the 3, the common denominator is going to be 15. So I'm going to have 20 over 15 minus 9 over 15. And for the x's, the common denominator is going to be 30. So just double check. 5 times 15 is 75 over 30. I'm sorry, guys. That was supposed to be a plus sign right there. Plus 20 over 30 minus 6 over 30. Alyssa.
Why is that added?
Because those two are in the numerator, so they're being multiplied together.
Oh.
Is that did it?
Yep.
Okay. All right. So 15 minus 6 is 9/10. And then 20 minus 9 is 11/15. And 75 plus 20 is 95. Minus 6 is 89. Everybody so far so good? Now, the 2 is fine because the exponent there is less than 1. There's no more simplifying I can do to that, so I could turn that into its radical form now. 11/15 also less than 1, so there's no more simplifying to do there. So I can turn that into its radical form. And then 89 over 30, though, is greater than 1. So this one could be simplified a little bit more. Now, the easiest way to handle that is with it still in this exponential form. So what I'm going to do is I'm going to rewrite 89 over 30 as a mixed number. So 89 over 30 is really 2 and 29/30. Is everybody okay with how you do that? We're going back to like elementary school skill here, but it's been a minute, so if you don't remember, please say something. That one's pretty easy to see, though, because the denominator is at least an easy number to deal with, right? And then if I use that product property again in the reverse direction, I can rewrite that as x squared times x to the 29 over 30. Now that's subtle. Let me just rewrite this and be a little bit easier for you guys to see what I did. So this is like that side, and then this is like that side. So I'm kind of just using this to go that direction. You guys see that now? And that just makes the simplifying a lot easier than trying to break up that x squared into like piles of 30, or that x to the 89th into piles of 30 when you've converted into a radical. I'm just going to skip over having to like simplify a radical because I'm going to deal with it while it's an exponential. So if I put this together, x squared, 10th root of 2 to the 9th, 15th root of 3 to the 11th, times the 30th root of x to the 29th. And that would be okay for me. That would fit the criteria. The other way you could have written this, or might see this appear in like a multiple choice test, might be something like this. Take a moment and see if you can figure out kind of how I went from our answer to that other answer. If I look at the indexes, the least common multiple of 10, 15, and 30 is 30. Right? That's the smallest number that each one of those three numbers divides evenly. Cool. To get 10 into 30, I need to multiply it by 3. That gives me the 27. To get 15 to 30, I had to multiply it by 2. That gave me the 22. And to turn 30 into 30, I didn't have to do anything. So that's the 29 stayed the same. So either of these answers is perfectly appropriate. They both receive full credit from me. It doesn't matter to me which one you give me. I just figured I'd mention that they're two representations kind of meaning the same thing. They're both equally reduced. But it's a little bit, until somebody kind of shows you what's going on there, it's not super obvious. The idea here to go straight to this would have been back here to find a common denominator for all of the fractions all at the same time. So if you looked at all the denominators, 2, 3, and 5, the common denominator you would have chose would be 30. And then if you carry that all the way through, you'd end up with the same spot as I did there. And that's fine to do. If you want to go that route, that's also okay. I think it's less obvious than what we did, which is why I didn't start with it. But okay, let's do one more of these big complicated examples, and then we'll probably call it a day. Sound good to you guys? Okay. And just for your reference, I'm going to decline on giving a homework assignment for this until after you've taken the other test. So I'll just have an assignment ready for you that you can start when you finish the test so that you're not tempted to distract yourself before then. Is that okay? I don't imagine anybody's going to object to not getting homework right away. It's like, no, I strenuously object. I need more to do right now. No? Nobody wants to go on that? No? Okay. All right. Well, you never know. Some of you guys are crazy. I've looked at some of the schedules people have signed up for. It sounds like alphabet soup, where every class starts IB or AP or whatever. All right. Let's think here for a minute. Let's do... All right, let's try this. So let's say we have the cube root of 10x times the 7th root of 96x to the 5th divided by the square root of 900x to the 10th. Again, the first thing I'm going to do is just the prime factorization. So 10 is just 2 times 5. 96 is 2 to the 5th times 3. And then 900 is is, yeah, that's fine, whatever. We'll get it with the x's. 2 squared times 3 squared times 5 squared. Oops. Forgot to write that 3 there on the first radical. So far, so good. Again, all I did was a prime factorization there. I did it mostly in my head. I double checked on my calculator, but if you need to write out the factoring tree on those, no big deal, right? Is time consuming. Nope, we have lots of time because we get out later today because of the altered schedule.
I think it is 2025.
Oh, is it?
Yeah.
Oh, okay. Well, you'll get to finish this one on your own then. See if you can finish it. Remind me next time when we can pick up where we left off on this so we can see what it looks like. But give this one a stab on your own.